is yes, right? Whenever something is given by linear stuff, it looks like it's a it should look like it's a subspace, right? Okay, so right, how does one check that whether something is a subspace? Of course, to do this, one uses the subspace test. And as you probably remember, the subspace test consists of several conditions, right? So the first one would be, of course, to check whether the zero vector is inside your subset, right? So the first one is this one. Well, let's see what's happening here in our case. Well, if I just substitute, so what's a zero vector? Well, a zero vector in this case is just 0, 0, right? Because it's a standard vector space C2, right? And so, well, one may wonder, okay, whether this 0 belongs to W. Well, in order to answer this, well, let's just substitute. Yeah, so look, I mean, here we have the description, and our pair of numbers, of complex numbers, indeed of complex numbers, right, belongs to W if it satisfies this equation. Well, let's just substitute. Let's just put 1 times, what is A1? A1 in this case is 0, right? Then, well, we have minus I times A2. What is A2? A2 is 0. So, of course, the answer in this case will be just 0, right? 1 times 0 minus I times 0 is 0. So it's okay. It satisfies. So meaning that 0, the 0 vector belongs to W. Okay, second. Well, let's now look at the sum. Yes, so the next property of the subspace test is asking whether, well, whether, say, for given two vectors, say, I don't know, say, V1 and V2 in W, whether it's true that the sum is again in W. Okay, so now again, let's substitute. So V1 is just, say, this vector, A1, A2. Now V2 is this vector, say B1, B2. Again, all this A1, A2, B1, B2, they're all complex numbers, right? And don't forget that we assume here that V1 and V2 are already in W. So meaning that they both satisfy this equation. So let me write it. A1, so we know that A1 minus I A2 is 0. And we also know that B1 minus I B2 is 0. Okay, so now, well, let's look at the sum. So what's the sum? Well, we just need to add these two pairs here, right? Okay, so it's A1, A2 plus B1, B2. What's this? Well, we just use the standard vector addition, because remember, this is a standard vector space. Meaning that, as I explained during the last lecture, so it's a, well, if you wish, it's a product of two copies of C, or equivalently, it's a direct sum of two copies of C, right? And what's a vector addition? Well, the vector addition is just given by coordinate-wise vector addition, right? And the scalar multiplication is given also by coordinate-wise scalar multiplication. So in this way, the addition, since I want to add them, so what's the result? The result is coordinate-wise addition. A1 plus B1, A2 plus B2. And now, well, this is my vector. Now what I'm asked to do, I'm asked to verify whether this vector satisfies this equation, right? Okay, so let's substitute. So I get the first coefficient, that's a1 plus b1. Maybe I should put it in the brackets. Then I need to put minus. Then I have I times the second, a2 plus b2. And well, let's expand it. Yeah, so let's reshuffle the summands like this. So, well, I can also write it like this, a1 plus a1 minus I a2 plus b1 minus I b2, right? And then, well, I can put brackets like this. And what do I see? Well, I see that this summand, indeed, this a1 minus I a2 is the same as this one, right? So it's 0. And this one is also 0 because it's just right here. So meaning that the sum of two zeros is 0, so it's 0. So it's fine, right? So this vector satisfies the necessary, the desired equation. So this vector belongs to W again. Okay, so in this way we checked the second property of the subspace test. Now the last one, let me do the last one. Then the scalar multiple, okay, scalar C times V has to be again in the double. This is what we would like to check. Okay, so well, let's again describe what does it mean that V belongs to W. Well, V is a, well, it's a pair, right? It's a pair, say A1, A2 of complex numbers, which satisfy the condition A1 minus I A2 is 0. And then, well, let's look at this one. So what's this? This is just C times A1, A2. And since, again, we are in the standard vector space C2, this scalar multiplication is nothing else but the coordinate-wise scalar multiplication. So this is just CA1, CA2. Now, well, let's write down our equation. So CA1, that's the first coefficient, minus I times the second coefficient. And what's this? Well, of course, I can also write it down like this, C times A1 minus I A2. And, well, we already know that this expression is just 0 because of this condition. Yes, and so C times 0 is always 0. So meaning that, again, the scalar multiple, we showed that the scalar multiple is inside our subset. So the third condition is verified. It means that we verified all the conditions of the subspace test. So our subset is a subspace. Yes. Okay, so is there any question? Any questions so far? So for the scalar multiplication, I wrote C an element of F. Is this all right? Well, in this particular example, it's already mentioned that, so C square is a standard vector space over what? Over C. So the field of coefficients is C, right? So, you still need to write C belongs to C, because F is a general notation for a field of coefficients. Yeah, so you would like to specify that you deal with complex scalars, right? Yeah, because it's better, it's always, in this case, it would be right to write like this because you need to deal with complex numbers, right? Okay, good. So that was question 2 subspaces. Say U and W of a vector space. Say V show that or prove that the subset of V consisting of all differences say U minus V, U in U, and V in W is a subspace. Yeah, I think in some of the assignments there was a misprint, so instead of W there was occasionally V, but so please correct it, so it has to be W. Okay, so again, that's a story about subspaces, right? So, and again, in order to answer this, we'll just apply the, we need to apply the subspace test. So, okay, so let's start to do this. So first, we would like to check whether the zero vector is inside yeah, okay, maybe we would like, well, maybe I'll just introduce some notation for this subspace just for convenience. Well, let's denote it by some letter. So which letter? Okay, let's suppose that this is S. Okay. And well, the first part of, or as a first at the starting point, we would like to verify that 0 sits inside our subset, right? Okay, so what does it mean? Well, it just means that we would like to show that 0, this vector 0, can be expressed as a difference like this. And the question is how one can express it as such difference. Of course, the answer is clear. I mean, we can just write 0 equals 0 minus 0, right? So this is my U and this is my V. We just substitute, okay, I mean, you can have any linear combination here, right? And you still can substitute your U to be 0 and V to be 0. Yes. And then since U and V are subspaces, zeros, they have to be there, right? So that's just elements of U, of capital U and W. Okay. And so that's it. That's our 0. So 0 can be expressed as a difference of zeros. Yeah. Okay, second. Well, now suppose that we are given two vectors, say W1 and W2, or maybe I would like to use a different notation, not W, but say okay, let's still use W's, that's okay. So say given two vectors, W1 and W2, and so they belong to S. We know that if they belong to S, then the sum again have to be in S. Okay. So, well, okay, so what does it mean that W1 and W2 belong to S? Well, it just means that they can be expressed as differences like this, right? They can be written as differences. So, well, let's just write W1 as say U1 minus V1, where U1 is from capital U and V1 is from capital W. Okay. And also we can do the same for W2, U2 minus V2. And well, let's look at the sum. What we can do about the sum? Well, we can just substitute. So u1 minus v1 plus u2 minus v2. Yes, we just substitute instead of w1, we put this expression. Instead w2, we put this expression. And then we can just reshuffle a little bit and write it down in this form. So it's u1 plus u2, right? Minus v1 plus v2. Now look, I mean, this sum and here, because it's a sum of vectors from U, it has to be in U, right? Because U is a subspace. So this is in U. And here, well, again, I mean, the same story. You have two vectors and each of them is from W. So the sum has to be from W. So it's from W. So what we just did, we expressed W1 plus W2 as a difference of two vectors. One of them is from U and another one is from W. And that's finishes our justification, right, of the second property. Okay, so what about the third one? What about the third one? Well, as for the third one, we would like just to verify, we'd like to check that whenever we are given a scalar. So here we use F because we don't specify a field, so it's just a general field, right? Because we are dealing with vector spaces over some field. Yeah? And well, we pick up a vector, say W from our S, and we would like to show that C times W is a gain from S. Okay, good. So now, well, W is from S. W belongs to S means that we can express W as a difference, right, of say U minus V, where U is from capital U and V is from capital W. Well, but then look, I mean, if we just look at the scalar multiple of W, what do we see? What do we see? Well, we see we can just substitute, right? So it's C times U minus V. And well, we can just open the brackets. So it's CU minus CV. And then look, I mean, this vector, because it's a multiple, it's a scalar multiple of a vector from capital U, it's a gain in U. And this vector here, because it's a multiple of a vector V, which is from W, is a gain in W, right? Don't forget that capital U and capital W, they were taken to be subspaces already, right? So, well, now, what we just did, we expressed the scalar multiple of W as a difference of two vectors. One is from U and another from W. So meaning that this is in S. And we are finished. So there's another which satisfies this equality for all T. So F is even. And then the question is, what if you just look at the subset of even functions? So let's denote it by, again, let S be a subset of even functions. Be the subset of even functions. The one from the assignment. Yeah? Okay. And well, the question is whether S is a subspace. And well, again, since it's a question about subspace, it's a story about how does one apply the subspace test, right? So apply subspace test. And well, again, I mean, they're just those three conditions, those three properties. So on the first property, you need to check whether the zero is an even function. And of course it is. Why? Because what's a zero? Well, zero function is just a constant zero, right? So it's a constant zero, constant function. And of course, this clearly satisfies this equality because it's anyway it's zero always. So whatever argument you are taking, it's always zero. Now, well, the second condition, well, if I'm given, say, two functions, two even functions, f1 and f2, whether their sum will be even. And yes, the answer is yes, of course, because, well, what's the sum of two functions? Well, you can easily see that if I just look at the sum, f1 plus f2 of t is f1 plus f2 of t, right? That's a sum. And then, of course, since f1 and f2 are even, I can just substitute minus t plus f2 minus t, and that's nothing else by the sum of f1, f2 of minus t. Yeah. So, meaning that, of course, the sum of two even functions is even. And finally, well, the same story, I mean, the similar story, if you just take a scalar, we are talking about real valued functions here, so you need to take it from R and then multiply by f. Again, we just need to check what is CF of t. And we can, of course, put brackets like this, right? And then, well, since we were taking, okay, C is from R and F is from S. Now, well, let's just look at CF. So since we take a even function here, we can just substitute f of t by f minus t. Yes, can we prove both steps at once? Take f1 plus c f2 of t. Yes, you can do this. Yes, sure, you can do this. If you think it's easy for you, yes. So, right, so let me just say, okay, so here I can finish, right, just by looking at this identity, and then I can just write it down as f of minus t. And that finishes the justification. Okay. Again, right, I would like to stress that, of course, you can combine 2 and 3, right, by checking that, well, this condition V1, V2 from S and C from R implies that V1 plus C V2, so those are vectors, whatever, are from S, right? You can also combine these two conditions into that one and check this one. Okay. More questions concerning question 3? Okay, then I'm going to the next one, question number 2. Question number 2. Okay. So here just a story about functions, right? So you are given a set S, which consists of 0, 1, minus 1. It's a subset of R, so just real numbers. And well, you look at two functions, f and g, from where to where? From S to R, right? And then we would like to prove that, okay, so first of all, f is given by this formula, and g is given by this formula, so it's t cubed. And we would like to check that f equals g. Yes, be careful, because look, I mean, of course, these two functions are different, right? If instead of s, we put the whole R. the whole set of real numbers. However, here we restrict ourselves only to those three values, right? So indeed, to show that functions coincide, two functions coincide, is equivalent to show that their values coincide. Yes, their values taken, well, their values which run through all these numbers here, 0, 1, minus 1. Yeah? So we only need to use only, well, we are only using those three numbers. So we want to check that f of 0 is g of 0, f of 1 is g of 1, and f of minus 1 is g of minus 1. And that's it. You don't have to do something extra, right? So just those three numbers. And of course, this is the case. Well, if I just substitute the numbers there, 0 is okay, 1 is okay, minus 1 is also fine. So they all coincide. So meaning that the functions coincide. Okay. And maybe finally, yeah, the question, the question 1. So here we are given two functions. Again, it's a function question, two functions from x1 to x2 and from x2 to x3. And then, well, of course, we can form the composite. We can take the composite of two functions, right? So first we apply f1 and after that f2. Yes. So it's from x1 to x3. And then the question is, okay, what one can say about the composite if, say, we know that both f1 and f2 are surjective. Yeah? Whether it's surjective or not. Or say if both f1 and f2 are injective, whether the composite is injective or not. No, it's a similar type of questions. And to do this, well, you just need to look at the definition. What does it mean to be surjective? So it's really important to write down it carefully and formally, right? So it's not enough just to say, okay, so it's clearly surjective. I mean, this is not the proof. Yeah? You want need to say something. Proof. And well, again, well, let me just remind you, what does it mean for a function to be surjective? So f from xy is surjective. Well, if what's happening, if for each y from y, yes, there exists x from capital X such that f of x is y. Yeah. So surjectivity is precisely means that for each such, well, that each element of y of the codomain can be obtained from some element of the domain by applying our function f. So basically, say, suppose now, so we would like to show that if f1 and f2 are surjective, then so is their composite. How do we do this? Well, just carefully substitute this condition surjectivity into this description, right? Okay, so let's say, okay, so well, let's look at this. Let's look at the composite f2. So we claim that this one f2 composed with f1 is surjective, meaning that we would like to show that for each, say, x3 from x3, there exists an element x1 from x1 such that I'm just copying this sentence here, but well, right, just copying in the sense I'm just substituting. Instead of y, I take x3, Instead of capital Y, I take capital X3, right? And so on, just substituting. And well, such that F2 composed with F1 is X3. Yes? So here, this is just the same sentence as this one, right? But just for different sets and elements, different notation. Okay, so now, well, but then look, I mean, so we would like to show that for each X3, there exists an element of X1 such that this holds. But we know that we are given, well, we are given that, say, F2 is surjective, right? So for that X3, there exists some element, say X2 from X2, such that F2 of X2 is X3, right? Okay. Now, well, look, I mean, well, now we are looking at this element X2, and well, we also do know that F1 is surjective, yes. But since F1 is surjective, for that X2, there is some element X1 of X1, yeah, such that F1 of X2 is, sorry, F1 of X1 is X2. Now we combine these two observations, and what do we see? Well, we see that if we just apply, okay, let's just do this. So take our X1 that we found here, apply F1, then we get X2, right? Yes, that we found here. And then, well, let's just apply F2, and then we get X3. So we are finished, right? Because that's precisely what we want. We want to find such X1. So we just found it. That's our X1. And we found it in two steps. First, we found X2, and then using this X2, we found X1. And in both two steps, we use the fact here F2 is surjective and here F1 is surjective. So we kind of did it sort of in two steps, right? And the same story holds for, well, one may see that, well, just play around. The same story holds for injectivity.